So this is our second look at finding cumulative distribution functions for new variables, sometimes described as transforming continuous random variables. And these are the wordy examples because these are sort of less obvious. So you thought the last lot was quite challenging. This is a little bit more so. So let's have a look anyway. So finding cumulative distribution for new variables. We saw this slide last time. You'll notice what basically is going on is you start with an f of x, which was the PDF. Remember this? This is the PDF. We switch it to a CDF, a cumulative distribution function. The algebraic bit gets me a new CDF, and then I can differentiate to get a new PDF. Now notice the transformed variable y, the original variable x. So it's basically switching variables. And I suppose wordy questions are likely to come up on these as well. I've certainly seen them quite a lot in the exams, often the very last question of the exam. Xn is a random variable length of the side of the square. Okay, fair enough. It is equally likely to take any value between 1 and 3. So let's just set that up. So we're saying, I don't know what to do an integral sign. We are saying that f of x is equal to, no, it's equally likely to take any value between 1 and 3. So if you just think about that for a moment, if I drew the graph between 1 and 3, there's a set value of it. And anywhere else, I assume it's 0. Now that's too wide. I reckon therefore if that was a half and this is too wide, this would give me an area of 1. So this is a uniform distribution function, and basically it's got a probability density of a half for x is between 1 and 3. And if x is between 1 and 3, it's got this PDF of a half, and anywhere else it's nothing. So that I think it's trickier than it looks at. You're trying to find what this tells us. But anyway, we're after the area of the square. So the area of the square, remember x isn't, the square isn't this square, this isn't a square, this is a rectangle. We are talking some general square where it says x is the length of the side. So it won't surprise you that if y is the area of the square, our transformation in this example is y equals x squared. This is a link then from f to y. Now, last time I showed you the very first job is to find capital F of x. This is the CDF. And if we started with this PDF, we always try to find the CDF. So we did an integration. You pick your lowest number, 1, and it goes up to x. And it's basically a straightforward integration of a half dx. Now when I integrate a half, I get a half x. But I've got to be a bit careful because I've got to put 1 and x into it. And because it's 1, putting 1 into it does not give me 0 like last time. So put x into it anyway. First of all, I get a half x. Put 1 in, I get a half. And I take those two things away, so that's my answer. So f of x is a half x minus a half. Now remember what we want. We want, same as last time really, and there shouldn't really be much difference between one answer and the next answer when you're doing this. We wrote last time that g of y was equal to the probability that y is less than or equal to y. That's our definition. And from that I can get rid of that y and put in my x squared. So it's the probability that x squared is less than or equal to y. But do I want that there? Well, notice last time I had a bit of a problem last time, in as much that last time it was 1 over. This time it's not 1 over, it's just a squared, so I've just got to square root it. So presumably it's the probability, well, of x square root one side, square root the other side, so the square root of y. Seems fair. So this then can be written And I did this last time. Once I got to a point where I've got the probability of x, and x is on the left-hand side. Now, actually, I didn't do much work to get x on the left-hand side. Just had to square root it. But I can call this the function of the CDF f of x now. That's my definition, in the same way as g of y was this. Once I get to this, I can just go, all right, it's a function of f of root y. Now again, let's go back to what f of x says. F of x said it was equal to a half x minus a half. If I put x in, I half it and I take away half. So if I put in root y, that's a half of root y minus a half. That's what I'm going to write. I'm going to write a half of root y minus a half. Well, that seems very good. That's my g of y. I'll think about this in a bit. I don't think I've switched these round. I don't think I had to turn my inequality round. So I think it's probably fair to say that y has to be between 1 and 3 in the same way it was before. Now, bear that in mind when I come to do my g of y. If you recall, and I do want g of y, little g of y, because it says the PDF of y, so that's what this is. This is the PDF. G of y is the differential of this. So I just have to differentiate this. It's probably easier if I think of this as a half y to the half minus a half. And times by the power, that gives me a quarter, or y to the minus a half. Not of power. And the minus half disappears. So what's that look like? That actually looks like 1 over 4 root y. And again, I probably should write 1 is less than or equal to y is less than or equal to 3. Let's see what the answers say. 1 over 4 root y. Oh, the one thing I've done wrong there, I did do it wrong. And that's because I have effectively changed my x values, because y is equal to x squared. So to get my y values, I've got to square my x values. Silly boy. So just using my formula here, I should have remembered that this goes up to 9. Change the limits. But 1 over 4 root y is the right answer. So that's good. Notice that when the first time I did it, I thought that was quite complicated. You probably think it's quite complicated first time you've seen it. So I've just made a note in the textbook that you can see all that on page 143. Here's another question. This was an exam question. The radius r of a sphere. Now you may or may not know that. What does it want? It's the surface area of a sphere. So the surface area of a sphere has a formula 4 pi r squared. Now the radius of a sphere is a continuous uniform distribution. Actually, this is quite similar to the last one. So I can say that I might as well call it f of r, because we've got r for our variable. And f of r is a continuous thing. It says it's basically between 0 and 10. It's continuous. Now, again, it's got a width of 10. So it must have a height of 0.1, because 0.1 times 10 will give me 1. So the this should be lowercase f of r, just remembered, is basically, again, it's 0.1 between 0 and 10. R is between 0 and 10. And it's 0 anywhere else. So bear that in mind. What do I want? I want a cumulative distribution function and a PDF of a. And we've got this formula for a of 4 pi r squared. So bear that in mind. First job, find capital F of r. And you remember that we integrate 0 to infinity, 0 because it's the lowest number. And we integrate from 0 to infinity of my 0.1 dr. And obviously that gives me 0.1 r. Between 0 and infinity. If I put 0 in, I get 0 out. I've said infinity, it's just well, it's actually meant to be an r. Silly mistake again. Make lots of those today. So it usually goes from 0 to x. So 0 to r in this case. So if I put r in, I get 0.1 r out. Put 0 in, it disappears. So my answer is actually 0.1 r. Okay, so now I've got my f of r, my CDF is done. I now have to go through this standard routine again. I write g of a. So my new letter is a. So I'm going to write g of a is equal to the probability that a is less than or equal to a. I've got a formula which links now a to it. So I can quite easily write this is the probability that 4 pi r squared is less than or equal to a. And I want r squared on its own. So I say the probability of r squared is less than or equal to a over 4 pi. And I square root, a bit like I did last time actually, it's quite similar in that respect. It will give me the square root of, well, I'll probably easy if I write square root of a over, for square root 4 I get 2, but root pi. Notice I've tried to square each individual bit. And this is actually the right way around. I didn't have to switch anything around. So this I can just write, or in fact I'll write it here. This is the f of this thing on the right. This is root a over 2 root pi. Now remember what we do then, we go back to our f formula, which was 0.1r, and we say, well, hang on a bit, if f of r equals that, then f of root a over 2 over root pi, well, that's simply 0.1 times it. Now 0.1 is like a tenth of r, so I suppose I've got to divide it by 10. Whatever I do, I divide it by 10. So it becomes root a, root r, sorry. I'll get there eventually. Root a over 20 root pi, because the 2 and the 10 combine to give me 20. So that's what I've got, and I reckon it's root a over 20 root pi. Now, I of course want the PDF as well, and you should recall that to find now this, I've got to differentiate it. So G, because this is G of A, capital G. So if I want little g of A, I differentiate. And I've got over here that it is root A. Well, that, remember, is A to the half over some number. 20 root pi, that's just a number. So if I differentiate it, I bring the half to the front. So I think I've got a 40th of root pi, a to the minus a half, and I knock off a power, which I reckon is 1 over 40 root pi root a on the bottom. So it's probably written 1 over 40 root pi a or something like that, both of them rooted. Don't know what the answer is, so I'm going to have a look, a sneaky look. Hey, look at that, it's even worked. Okay, that's it. Again, think about the limit. We sussed this last time. Last time I had limits of 0 to 10. But I have, you'll notice, squared them. I've got now a is 4 pi r squared. So you can kind of see I've got to get my new limits, I've got to times by 4 pi and square it. So if I square it, I get 100. I get 400 pi in my mind there. And they get 400 pi as well. That's worked. Now that's, I think, oh, well, there was a little bit more to do, but I'm running out of time. So perhaps we'll finish that. And we'll also look at these where you can't quite see. It says maximum values. We'll look at that in lesson as well. But I think that's probably a safe place to finish. And in class, obviously, we'll finish off now exercise 7H. Thank you very much.